Now let us consider the following example, where D is a very nice region in the xy system bounded by 1. Now in Cartesian system, writing a double integral over this region would be very simple because it's a rectangle, actually a square. X changes from 0 to 1, y changes from 0 to 1. In either order, it would be directly possible. But here, firstly, D is not simple with respect to R first. Okay, this is because in here, when we start from the origin, move in all directions, that's the increasing R direction, okay? We are already inside in these cases, and we go up to this curve, and then we go out of the region. Or if we move at a different angle, we start from the origin, but we move out of a different curve. So the curve is not the same curve all the time. This means that we don't get a simple region. We have to decompose the region. Okay. Well, in other directions here, we are immediately outside, so they don't count at all. Now, when can we make R change from, it always starts from 0, and we are inside, from the 0, R equal to 0 curve, it's a circle with 0 radius, up to the same curve at the end. Well, because there are two curves, obviously, okay, we need to decompose D into something like this. Call this D1, call this D2. Well, now, if we look in the R direction, starting from here, okay, of course, it goes up to the same curve in D1. In D2, again, it starts from 0, goes up to the second curve, and this is always the case. So these are simple regions with respect to R first. Of course, in the meantime, clearly, theta changes from a constant to another constant. For D1, it starts from pi over 4, goes up to pi over 2. For D2, it starts from theta is 0, goes up to theta is pi over 4. So these are constant lines. It's okay. So let us write our integral on D1 in polars, in polar iterated form. Well, of course, R starts from 0 and goes up to y equal to 1 line. Well, y equal to 1 means in polars, okay, well, y was, remember, r sine theta, so, okay, r is cosecant of theta. Because y is 1, r sine theta is equal to 1, so r is cosecant of theta. Well, this then tells us that we have f. I will not write r cosine theta, r sine theta, just to save time. Okay. We have the r coming because we change into polars, and we use r first. So here, r changes from 0 to y equal to 1, which means r is cosecant of theta. And theta, in the meantime, in D1, change from pi over 4 up to pi over 2. Okay. And in D2, R now starts from the origin and goes up to x equal to 1 curve. Now, x equal to 1 means, okay, R cosine theta is 1. This is x. So, R is, okay, secant of theta. So, R changed from then 0 to secant of theta, and theta in D2 changed from 0 up to this angle, which is pi over 4. So you see, rectangles in rectangular coordinates were very simple to iterate, 0 to 1 and 0 to 1. That was it. But in polars, it's not even simple, and we had to work quite a lot. Okay. The converse, that is, if you have a circle or a wedge, okay, is also true in the following sense. If you want to write an iterated form on a circle or part of a circle, you have quite work to do because, okay, it may not be simple in the first place and you have lots of trouble there. But in polars, this is very simple to write because in polars, such regions actually are rectangles in the R theta system. So they become very easy to write. Let us now consider how we could write, okay, the same problem, but with respect to theta first. Okay. So let us write for in theta first iterated integral. Well, let us first look at what we have. In the xy system, okay, the theta direction, remember, was starting from the positive x-axis and moving counterclockwise. So, we start from here, okay, and then we move counterclockwise. We hit this curve. It's fine. We start from a curve in theta direction. Okay? And we hit another curve, and this is always true. Well, that's not correct. Because if you start from here, you are not inside. Now you're inside. You move in theta direction, and you hit another curve. So you start from a completely different curve, okay? And you go out again from a completely different curve. So there is trouble here. Therefore, this is not simple with respect to theta first. Okay. But we can make it, okay, simple by decomposing. How? Well, we want this rotation direction always give us the same two curves. It should start from the x-axis, go here. It should start from the x-axis, go here. Well, it's true so far. And until this point, it's still correct. But if you are beyond this point, okay, it will not be correct because you're outside. Now you're inside from a different curve and you go out again from a different curve. So the decomposition is clear, namely this circle is the boundary. In other words, let us decompose. Okay. Let us decompose the unit circle, okay, at this circle, okay, and call this D1 and call this D2. Now, D1 is simple with respect to theta first. Why? Because if we start from anywhere on the positive x-axis and move counterclockwise, we always start from theta equal to 0 curve, which is the positive x-axis, go up to the positive y-axis, okay, which is theta equal to pi over 2. But it's a curve, again. So here in D2, that is in D1. In D1, theta starts from 0, goes up to pi over 2. These are curves, the x-axis and the y-axis. What happens to r in the meantime? Remember, r should change between two constant values. And constant values for r means circles. So, in D1, r changes from 0 up to this curve, this constant, r equal to 1 all the time. So, okay, r changed from 0 to 1. Now these are constants. Okay. So, integral over d1 of f dA would be in iterated polars. Sorry, theta first, where theta is the first variable, from 0 to pi over 2, okay, from the x-axis up to the y-axis. They are also theta equal to constant curves, and r change 0 to 1. Okay, this of course says that this quarter of a circle is transformed into polars as a rectangle. And the rectangle is this, with sides, okay, 0 to 1 and 0 to pi over 2. So that's why we have here curves, but actually theta equal to constant curves. Now what happens in D2? Okay, remember, this is D2. Well, in D2, okay, indeed, we do have a simple region with respect to theta first, because when you look in the theta direction, okay, we are outside. Now we go inside, and we are outside again. And this is the phenomenon all the time. Namely, you always go from x equal to 1, leave from y equal to 1. So theta changes between the curve x is 1 up to y is 1. Okay, in the meantime, how does r change between two constants? Well, the first constant is clear, r is 1. Okay. Where do we leave? Well, it's this one, of course. Okay. And the radius is root 2. Okay. Well, does this look like a classical type of simple region for theta first? Well, yes, because you can think of this region as follows. This looks like the following. Okay. You have a curve here and another curve. These are theta equal to curves. and you have two circles. Okay. Circle r equal to 1, r equal to root 2. Now, this is a classical, okay, simple region with respect to theta first. Theta changed from, say, g of r up to, say, h of r. And r from 1 to root 2, they are constants. But here, of course, the 2 points, A and B, okay, namely, in our case, A is equal to B. Okay. Namely, on the second curve, okay, this point is A and B at the same time. They are the same curves. But it doesn't change that it is a special case of this general formulation. So it is simple with respect to theta first. Well, so the integral over d2 f dA would be f r d theta dr, and theta changed from, okay, x equal to 1 up to y equal to 1. But of course, we have to change them, translate them into polar language. This, of course, means that, okay, r cosine theta is 1, so r is secant of theta. We did this a minute ago, and this transformed into r is cosecant of theta. Because r sine theta is 1, so r is cosecant of theta. And r changed in the meantime, 1 to square root of 2, because it's a simple region, and r changed between two constants. Now, obviously, d1 union d2 is d, and so this decomposition is well defined. Okay. Well, a similar example, say example 5, is where D is an intersection of two circles with radii 1, as follows. Okay. And these are 1s. And these are circles with radius 1 and centered at 1, 0, respectively, 0, 1, and so on. Okay. And D is their intersection. Okay. Now, when we look at these curves, and this figure actually, we immediately see that D is not simple with respect to R first. Okay. Why? We start from the origin, okay, move in all directions, that is R directions. We are outside here, and we are inside, and we leave from this upper circle, or if we move in this direction, we go out from the other circle, which means that the point where we leave our domain is not given by the same curve. Well, this means it's not a simple region, and we have to divide. Okay. So let us decompose D. Of course, how do we decompose it? Well, okay, because the two circles are different, we have to show this difference, hence divide it in such a manner. Okay. You can call this part, say D1, and this part D2. Now, D1 and D2 are both simple regions with respect to R, because starting from the origin in D1, you always leave from this circle part, this arc, which belongs to the lower circle, and the opposite if you are in D2. And so, both are simple. With respect to R first. Which means that we can write iterated integrals in polars for them. So let us look at this. By the way, this way of writing in iterated form has nothing to do, okay, with area or volume, because everything depends on what f is. Okay, f may not be positive, okay, and you cannot argue as follows: D1 and D2 are symmetric. Well, they have the same area, yes, but what does f do on top of them? It may not be symmetric, so you cannot multiply by 2. So symmetry arguments here won't work, okay, because you don't know what f is. Okay, so we have to take the trouble to write them separately. Well, in D1, we said that R starts from the origin, goes up to the lower curve. The lower curve is a circle centered at 1, 0. In other words, okay, the lower circle, namely this one, okay, actually, I'm not interested in the region, okay, just the curve. This curve is given by x minus 1 squared plus y squared is 1. Its radius is 1, center is at 1, 0. Okay. Now, what does this mean in polars? Well, to do that, let us open this up. That is x squared minus 2x plus 1 plus y squared is 0, okay, is 1, sorry. And 1's cancel out. And we know that x squared plus y squared is r squared minus 2x, that is 2r cosine theta, this is x, that is 0. So we use the conversion formula. Well, that means, of course, that r is 2 cosine theta. Well, we canceled r's, okay, because we assumed r is not 0. What happens if r is 0? Well, it is taken care of by the value of theta, which is 0. So we can assume that it's not a loss of information. Well, similarly, okay, we will need that in a minute, so let me derive that. Similarly, okay, this circle with radius 1 becomes, of course, a circle of the form y minus 1 squared is 1. And similar to this, instead of x, we have y, so it becomes r squared plus, rather minus 2y, which would be r sine theta. This is 1. Okay. And that would be 0. So r would be 2 sine theta. Okay. Now, with this information, we can now go back and write down our iterated integral in polars with respect to r first. Now, in D1, r changed from 0 up to the lower circle, which was 2 cosine theta. And theta, okay, changed from, in D1, Of course, it starts from this diagonal, x equal to y, goes up to the y-axis. Well, in polar language, it means from pi over 4 up to pi over 2. Now for d2, well, this time r changed from 0, okay, but we leave from the upper circle, which was 2 sine theta. So I'm not repeating the whole thing. And theta values for d2 start from 0 and go up to the y equal to x line, which is pi over 4. So similar to the first case, we can formulate this. And then, of course, we write integral d would be integral d1 plus integral d2, because d1 and d2 are disjoint except on the boundary, and we know this property of double integrals. Okay. Now, let us write the same integral with respect to theta first. Okay. Call it phi prime. Okay. What do we have? Okay, recall we had a circle, okay, and we had a circle here. Well, let me do it appropriately. Something like this, okay, and this is the D. Now, if we move in the increasing theta direction, okay, counterclockwise, of course, we start from the x-axis, and because this circle is tangent to the x-axis, when we increase theta from 0 to something, we are immediately inside. Even when theta is 0, we are inside. Okay? That means we start from this curve and go up to this outer curve. So we start from the top circle and leave from the bottom circle. Well, does this change if I change my angle like this? No, it doesn't. Either we are completely outside, or if we are inside from the correct curve, and we always go out from the same curve, which is this one. In other words, and of course, r changed from 0 up to this circle, okay, which has, it's not a very accurate picture, but you can see that, which has a radius of square root of 2. And so, indeed, okay, this is a simple region with respect to theta first. Okay. Because theta changed from the upper circle up to the lower circle, and r changed from 0 to square root of 2. So we get directly the integral over d without any decomposition, because we don't need it. Okay. And theta changed from, let me check, upper circle, which was 2 sine theta, up to the lower one, which was 2 cosine theta. In the meantime, r changed from 0 to square root of 2. Of course, this becomes a simple region with respect to theta first, because these 2 points are actually, could be separate points, okay, connected by a circle, by an arc, but they coincide. As in the previous case, we have 2 coincidences here, namely, we have our theta changing this way, and our r changing from this circle up to this circle. Okay. But these 2 points, A and A prime, are equal. These 2 points, B and B prime, are likewise equal, and so you get this curve. So, using theta first sometimes makes the job easy. Okay. Well, at this point, an application which I will call a remark. Okay. Namely, this is an application to finding areas. Okay. In polars, of course. Okay. Consider the following. Okay. Consider, for instance, very simply, okay, AB and a positive F. Okay. Then this area was A to B, F of X dx. Okay. Now in polars, what do we have? Of course, here, note that our y variable changed from a curve to a curve. Okay. In polars, and the other one between constants. So these are straight lines here. Now, in polars, if r changed from 0 to a positive value, okay, the other variable, theta, should change between 2 constants. So, in polars, this looks like, well, again in the xy system, I'm making my sketches in Cartesian system. This means that you have a curve which is r is f of theta, and you have 2 constants for theta, theta 1 and theta 2. And this is your region, which very much looks like the top one. Of course, this is simple with respect to r first, and so, okay, we can calculate the area here. Namely, the area is the double integral over d, if this is my d, of 1 dA, which, because it is simple with respect to r first, okay, it becomes 1 r dr d theta, and r changed from 0 to f of theta, and theta from theta 1 to theta 2, something like a to b. So it very much looks like that. But here we have an extra r. When we integrate, this becomes theta 1 to theta 2 of r square over 2. So we take square of f. So this is the area formula. That's to say, okay, theta changed between 2 constants. We have a curve here, and we square it and integrate, and then we get, indeed, the area in question. Okay. Well, let us apply this to an example. Okay. Well, the area of a circle. Okay, with radius r. Now, this, of course, is this. This is my d in xy system all the time. Okay. Now, so area would be theta 1 to theta 2. Recall, you start from here, okay, and you move in counterclockwise direction until you get to 2 pi. So theta changes between the two constants, 0 and 2 pi. And f of theta is r. So this is r squared over 2 d theta, which of course says that it's r squared over 2 times 2 pi, as we expect it to be. Okay. Well, one generalization, if you have a region bounded by two curves, one bigger than the other, okay, then recall if we had another thing here. So this time consider the following figure. Okay, we have A and B, we have some say g of x and some h of x. Okay, they need not be positive or negative, but okay, g of x is smaller than h of x. Okay, then okay, we know from 119 that area would be a to b, g of h of x minus g of x dx. Now, how does this carry over to the polar formula that we just derived? Of course, you are talking about a difference of areas, and so you have to square them. But there's some trouble in here. Namely, if you have negative values, when you take the squares, okay, they may become the same and they can cancel each other and the area would be 0, but it's not. Okay, think of something like y is minus x and y is plus x. When you square them, or r is minus theta and r is plus theta, when you square them and take the difference, you have trouble. So this does not directly carry over to polars, but this becomes the following. Okay. If some g of theta and you have h of theta, then okay, the area in question, that is something like this, this would become theta 1 to theta 2 if these are theta 1 and theta 2. And if these are g of theta, and this is h of theta, okay, then you have 1/2 of the difference of the squares, as you can expect. So take this as a remark. It may make calculations easier in some cases. For example, if we want to calculate the area inside a cardioid, so you can check that as an exercise. Okay, find the area inside a cardioid. Say r is 1 plus cosine theta. R is always positive, so you can check it directly. We will have an example similar to this in a minute. Okay, now our next application will be to finding volumes, right? Finding volumes. So we will continue our examples actually. So this will be, okay, let me say examples. Okay. Of the solids given. Now, before we venture into concrete examples, we already mentioned that, but let us recall the following. Okay. If we have a solid which looks like the following, okay, we have okay, a top part, a surface at the top, z is h of xy, and a part, okay, at the bottom, say z is g of xy, okay, and the sides go vertically down. So we have the vertical sides, and at the bottom we have some region D. Okay. Now, volume of S would be, of course, here we assume that h of xy is greater than g of xy, as the picture suggests. This would be directly double integral over d of h minus g dA. Of course, here the sides are vertical. Okay. Namely, when you look from the top, okay, you see D at the bottom. Now, it is not specific to Z equal to all the time. Okay. Clearly, variations are possible. Okay, are certainly possible. For example, okay, consider the following picture now. Okay. Say these are your x's and y's, and so on. Now, suppose when you look in the x direction, okay, you have some surface, but in the x direction you have vertical lines, okay, surfaces, and at the bottom you have something like this. Okay. The first curve, surface, would be x is h of yz, and this one would be x is g of yz. And if you move further, you get a certain d here, which is on zy plane. Okay. In other words, if you rotate this so that it stands vertical, it would look like this one. Then, of course, volume would be integral over d of the larger one minus the smaller one, the larger one in the x direction, so it is h minus g dA, etc. Okay, such variations are certainly to be expected. Okay, now let us go to our examples. Well, we want to find the volume of a sphere of radius r. Well, we found this a few times, if you remember, even by using definite integrals, but there we had to use some transformations, namely some substitutions, inverse trigonometric substitutions, and such things. Okay. Now we will see that it's much simpler if we use polars in double integrals. Namely, what happens? Well, obviously, this is, okay, a circle here and a sphere here, which, say, is x squared plus y squared plus z squared is r squared. And so the radius is r. This is the upper part. So this is the upper hemisphere. Okay, why? Because we want to use the symmetry. Actually, it doesn't matter at all. But then volume would be 2 times, okay, the double integral over d of, okay, the height. Well, the height is root of r square minus x square minus y square dx. Okay? Because this is a positive function, okay, we get the volume below it above the xy plane, but we multiply it by 2 because of symmetry and so on. Now, what is d here? Clearly, d, if you look at a sphere from the top, what you see is the largest circle in question, and therefore d is nothing but a disk of radius r. Now, with this information, let us calculate this volume. So volume would be twice now an iterated integral in polars, of course, because circles go well with polar coordinates, vice versa. So this is the square root of r squared minus r squared. So it seems that we need an inverse trigonometric type of substitution, but we don't, because in polars we have this term coming and dr d theta. Now, on d, how do r and theta change? It's a circle, so r changed from 0 to capital R. Theta makes a full revolution. Okay. Well, this directly tells us that this is 2 times 0 to 2 pi. Now integrate. Here you have the derivative of r squared. So this is r squared minus r squared. Okay. 3/2 divided by 3/2. Add 1 and divide. Of course, you have minus 2 somewhere here. And this happens from 0 to r. And you will integrate with respect to theta. Well, at 0, okay, at r you have 0, so at 0, because of this minus, you get a plus thing, and you get 1 over 3, okay? When r is 0, you have r cubed. Okay. Now what remains? You have 2/3 r cubed times integral would be 2 pi, so you get the desired result in a very simple way. Okay. Well, as another rather standard example, that is, I said find the volume, but anyway, find the volume of the solid, okay, S bounded by, okay, Z is 1 plus x squared plus y squared, and x squared plus y squared is 4, and Z is 0. Well, in all geometric problems, it's always a good idea to see what we're dealing with, namely make a rough sketch. Okay, when we look at this, we see that there is no Z here. It's a cylinder which goes up and down with radius 2. So, in here, okay, we have a cylinder which goes down and up like this. Okay, this is x squared plus y squared is 4. Okay. Well, what do we do with these sides of the cylinder? Well, this is the sides of the cylinder. Inside is empty. So when I say cylinder, it's not an elementary cylinder. I mean in elementary geometry, which is full. These are just the surfaces. Okay. We cut it from top and bottom. Well, clearly, 1 plus x squared plus y squared is always greater than 0. So this is the top one. Okay. Well, it's a paraboloid. Because of 1, it's shifted up a little bit, up to the level 1, and it's a paraboloid of this form. Okay. And at the bottom, okay, we have a plane, z equal to 0. So what happens? Okay, we have a cylinder, we cut it from the bottom by z equal to 0. From the top, we bound it by a paraboloid. Okay, so if we make the picture in a better way, it looks like the following. Okay, this is the z equal to 0 level, and at the top you have a paraboloid cutting through it. Okay, so this is, okay, bounded by the paraboloid at the top by z equal to 0 from the bottom, but this part is empty. Okay, because the paraboloid is just carving some piece of it. We look at what happens below it. Well, this immediately says that the volume would be double integral over d, which happens to be the base, of course, of the difference. The difference is, of course, 1 plus x squared plus y squared. That is the paraboloid, minus 0, but we don't write it. It's dA directly. Now, because we are dealing with a circle at the bottom, of course, it's a good idea to use polars. So this becomes, in polars, 1 plus r squared, okay, r dr d theta. And because d is a circle with radius 2, it starts from 0 to 2 and 0 to 2 pi, and you can easily evaluate this. Okay. Well, a slightly more complicated example is a solid bounded by these two curves. Okay. It's bounded by x squared, y squared, z squared is 2a squared, and from above. We have to be careful about these wordings. Namely, well, when it says bounded by this from above, it points out that possibly there are more than one solids bounded by the given surfaces. And this directs you to which one to take. So you have to keep attention to them. And, okay, by x squared plus y squared is az from below. Okay, here a is a positive number. Okay, find the volume. Well, it's a good idea to review the quadrics a little bit for these visualizations, because it always helps to make a rough sketch. Firstly, the first one is a sphere. A is a positive number, and it's a regular sphere centered at the origin. The second one, z is x squared plus y squared up to a constant. It is a paraboloid. So we have the following. Okay. We have a paraboloid. Well, okay. This is the paraboloid. These are my x's and y's. This is my z. And I intersect this with a sphere. Let me say a large sphere like this. Okay. So as you can see, a paraboloid surface cuts two solids from the sphere. One is this part, the other one is the below part. Okay, if you carve a sphere, you get, of course, two pieces. Now, this characterization tells us that from above we will have the sphere, and from below we will have the paraboloid. So it is this one. Now, to make a better sketch, of course, we have the following. We have, okay, a sphere, and we have a paraboloid. Okay, I'm sketching a cross-section here. And of course, they intersect at some point, at some curve. And so, the solid in question is this. Okay. At the top, you have the sphere. At the bottom, you have the paraboloid. So, the volume of S would be the integral over d of the bigger one minus the smaller one. The bigger one is the sphere minus the paraboloid. Okay. So, the sphere, of course, it is the positive z part of the sphere. So, it's the root of, okay, 2a squared minus x squared minus y squared minus the paraboloid, which is z equal to x squared y squared over a. So this is the volume in question. Now, what is d? Well, d from this picture directly is this one. As we see, it is this part. Now, what determines d is the circle around it, its boundary. And this circle is clearly the same as the circle at the top, which is given by this one. But this is the intersection of the paraboloid and the sphere. So, d is given by the circle of intersection. It's a circle, as we will see in a minute. Of the paraboloid and the sphere. So, let us equate the two. Okay. Namely, it says that we have x squared plus y squared plus z squared is 2a squared. Okay. And x squared plus y squared is a squared. This is the sphere. This is the, that is az. This is the paraboloid. So when we equate them together, okay, we see that we have, let me check my numbers again. So we get 2a squared is right. Right. Yeah, that's okay. Yeah, so we have z squared plus az minus 2a squared is 0. Or if you want, we have here z minus 2a plus 2a and z minus a. Okay, is zero. But of course, this is not possible. Namely, equal to 0 is not possible since z is positive. Okay, z cannot be negative. I mean, a is positive. A is positive and z cannot be negative. I have to say both, since a, z are positive. So z must be equal to a. And when z is equal to a, it doesn't matter which surface you look at, they will give you the same thing because we calculated the intersection. When z is a, it means that x squared plus y squared is az. This is a, so it is x squared. In other words, the intersection is a circle with radius a. Okay. Now, with this knowledge, then we can write the volume as an iterated polar one. Why polar? Because we have a circle here. Okay. Well, in writing it in polars, we have square root of 2a squared minus r squared minus r squared over a r dr d theta. On a circle, polars are very simple. 0 to a, 0 to 2 pi. And the rest can be easily calculated because even though you have a radical here, a root, you have r multiplied. So it's just a simple substitution. The other one is a polynomial. And so this can be calculated. Makes the job easier to use polars. A last example in these discussions, actually this will be a nice extension for which at this point we don't have any justification. Okay, but okay, one can do it theoretically. Just let us continue with our example. Okay, so a last example. Okay, assume that we know the theory of double integrals, even though the domain is unbounded. That is, suppose we know improper double integrals. Well, of course, there are such things. For instance, if you evaluate a double integral over not a circle or a square, but over the first quadrant, well, then it becomes an improper double integral. Assume we know how to deal with them. So assume what we did so far extends to unbounded domains. Okay. So to improper integrals. Okay. We assume this. Okay. Then we can apply what we know so far to a particular example. Namely, consider this. 0 to infinity e to the minus x squared dx. Well, from our considerations in 119, in improper integrals, we know that this integral converges. Okay, this, okay. Then we know it converges. From 119. So let I be the value. Well, then I can write I square as 0 to infinity e to the minus x squared dx times 0 to infinity e to the minus y squared dy. Now, of course, changing the symbol in the integral from x to y doesn't change anything. So it is indeed I square. Okay. But we can put them together as follows. Now, this is a constant. I can put it inside this integral. Okay. So it becomes 0 to infinity, 0 to infinity. It's an iterated integral. E to the minus x squared minus y squared dx dy. It's an iterated Cartesian integral, but the domain is clearly not a bounded one. Actually, the domain is the first quadrant. Okay. Here, if D is the first quadrant, okay, thinking it as a rectangle, an unbounded rectangle, we get integral d e to the minus x squared minus y squared dx. Namely, think of the first quadrant as a rectangle. How would you write an iterated integral on that rectangle? Of course, the sides go 0 to infinity, and so you would write it this way. Well, all these, of course, need justification mathematically, but we assume we can do such things at this point. Now, the point is, well, this very much invites us to changing the variables into polars because we have x squared plus y squared. Let us do it. Because it's a rectangle, okay, and in polars, r starts from the origin. Well, think of this d. D is the first quadrant, okay. R starts from here and moves in all directions, and it goes up to infinity. Namely, you can think of this as it's bounded by a circle with radius infinity. Okay. Of course, this is a little bit too much on our imaginations, but if you think of this okay, as an infinite rectangle, you can do all these things. Well, then r changed from 0 to infinity, and theta changed from 0 to pi over 2. Okay. But the point is, we can evaluate this integral now. It is nothing but, okay, e to the minus r squared divided by minus 2, 0 to r, limit r going to infinity. It's a single improper integral. And we do this. Well, what does it say? Obviously, it says that if we have r, okay, we have e to the minus r squared here, and minus 1 divided by 2, and then we have the limit r going to infinity, which just gives us 1/2. So this is 0 to pi over 2, 1/2 d theta, which is pi over 4. Okay. But this was I squared. So I, 0 to infinity, e to the minus x squared dx would be root pi over 2. So in an interesting way, applying the polars, we could evaluate the value of this integral. Indeed, it's correct. Okay. All these things that we did here can be done. There is a theoretical justification for them, which we are not familiar at this point, and we will not be familiar at this point.